here. Okay, so this would be a very typical sort of RBR CTD. And so, you know, we do build CTDs for different pressure ratings, and the construction. The construction differs very slightly between the three different pressure ratings that we have. So we have the one version that goes to maximum of 750 decibar, and then we have a 2000 and a 6000 versions. You can see they vary slightly in the construction. Just as you go deeper and deeper, you require sort of more a more robust construction to handle the increasingly high pressure. Let's time then to get into a little bit of the operating principles and how the inductive conductivity cell works. Okay, so we go back to our university physics courses, and we have to remind ourselves what Faraday's law of induction is. I had to do the same, but that's the basic principle of the cell is that we're gonna induce basically an alternating current in the seawater. So what we have is Faraday's law says that we have a variable magnetic flux that drives a current within a circuit. So you think of that sort of classic physics experiment with a bar magnet being passed through a loop of wire, and how if you move that bar magnet, it induces a current. That's sort of that's the basis of this technology. RBR uses a particular, there are different ways to implement this in a conductivity cell. You can use a single coil, a sort of single transformer design. RBR uses a double transformer design. So there, within this cell, I'll show another picture. There are two independent coils, toroidal coils. So ferrite rings that are wrapped with a wire. And this is not. It almost seems silly to say this is not new. This is 100 years old. Picard and Frouvold were Swiss scientists who actually wrote about this in the 20s. This is the Picard of the famous sort of Picard family that had many scientists who developed, you know, the bathysphere, and were really into hot air ballooning apparently. And then, you know, 20 years later, sort of more or less independently, a fellow, M.J. Rellis, who was a student at MIT, wrote a master's thesis on using electrodeless method for measuring low frequency conductivity electrolytes. Okay. And if you're curious, the links to those papers are below. The Picard and Frouvold one is in French, of course. Yeah, so getting back to, again, sort of how they work. So within the cell, there are two toroidal coils, coils of wire wrapped around ferrite rings. So what there's a sort of what we call a drive coil and a receive coil. So we're gonna apply an AC current to the drive coil. This is gonna cause a changing magnetic flux in the ferrite. And then this will induce an electric current in the seawater, electric field, and therefore an electric current. So that AC current in the seawater will then induce a magnetic flux in the receiving ferrite. So if this, let's just say, doesn't actually matter, but say this is the drive, it's the drive coil, and this is the receive coil. So we generate the field with this one, say, and then that field is picked up by the receiving coil. Okay, and that changing magnetic flux inside the receive coil drives a current, drives a magnetic flux in the ferrite, which drives a current in the receiving coil of wire. And it turns out the response, the current that's driven within that coil, the receiving coil, is proportional to the seawater conductivity. Actually, the conductance, but you can transform that to conductivity with the cell constant. Okay, and so that's the basic principles of how an inductive cell works. Um, you know, so this technology has some advantages and disadvantages. So you know, we'll start with the pros here. Uh, you can build these with a low aspect ratio, and that just means that the the hole within the cell through which seawater passes can be relatively large compared to the length. What this means is that the cell flushes naturally. And the consequence of that is we don't require a pump. And the consequence of that is that the power consumption is low. And also without pumps, these CTDs can be made acoustically quiet, so they're good for use, particularly on gliders when say you have past acoustics that require a sort of acoustically quiet environment, or on say if you're measuring turbulence, which is shear probes. It's a robust, stout design, and then inductive cells. This is something that was recognized very early on. Are contactless. That means there's no metal electrodes, so there's no chance in um, um, we were relatively insensitive to surface oils, and the electrodes can't corrode. Sorry, excuse me. Electrodes allow the possibility of corrosion. Say but you have to platinize them and so forth. But so that's an advantage of the inductive cell. Of course, there's a disadvantage, and I think the main one here that we'll discuss in some detail is the so-called proximity effect, and that is because the field induced by an inductive cell reaches outside of the cell itself. Ideally, you'd want to keep the field confined to the inside. That does mean that any sort of object, such as a mooring line, say here, can interfere with the measurement. Okay, so that's the main disadvantage of an inductive cell. So, but we're going to discuss that and show that in fact is generally not a particularly strong limitation to science you can do. Yeah, so let's discuss the proximity effects a little bit. So the first point I want to make here is any material near the proximity of the cell will change the measured conductivity. Okay, and so a rough estimate, then the number that we use is we ask that any 15 centimeters of the cell, anything within a radius of 15 centimeters of the cell be kept clear of any object. Okay. So here's an example. Well, okay, let's just move on. If you introduce a conductive material, a highly conductive material inside within the sort of 15 centimeter radius, you will bias the value high, okay, because metal is conductive, or like a stainless steel cage. But if you have, say, some kind of insulated mooring line or rope of some sort that's introduced near the cell, you may bias the measurement low. And in fact, the change in conductivity is not an offset; it's a scale factor. So keep that in mind if you ever find yourself needing to account for this in some way or another. These are usually fixed by a scale factor and not an offset. But the one thing about this is that it doesn't mean we can't have objects near the field. It just means that the instrument, if you wish to have a cage around your CTD, such as in this photo, or or if you're building an Argo float and you need to have an iridium antenna or an optode near the cell, you just need to calibrate this conductivity with any kind of object that will be used in the deployment. It just needs to be calibrated thusly. So in this case, here's a CTD. This is an older generation of a deep cell we made, but there was no issues with the conductivity measurement here because this actual conductivity cell was calibrated with this protective frame in place. Okay, with these struts. And the last thing to point out with this is that the air-sea interface, in fact, makes a difference too. So, but we've done some experiments, and we know that we can measure conductivity to within our accuracy specification with 0.003 millisiemens per centimeter, all the way till 10 centimeters from the surface. So if you have a float and it reaches 10 centimeters from the surface, you'll still get very accurate readings. I got a question. Can you share the calibration procedure to eliminate the proximity effect? Yeah, we can. Maybe we can discuss that after I finish off the slides here. That's okay. Okay, so just moving on again. So to put some numbers to this, for example, a common concern is, when profiling, it's relatively easy to keep the cell free of any objects nearby. In mooring applications, it's a little bit trickier because of the mooring line, but it turns out that the errors introduced from, for this example, an insulated steel mooring line are actually quite small. We can offer different clamp, RBR can build different clamps, or offers 2 different clamps, so here's a 75 millimeter clamp, and here's a 150 millimeter clamp. And the errors you get from, say, from introducing this mooring line are relatively small in this case. And so in the case of 150 millimeter, we're looking at an error that's almost undetectable in salinity. Okay, I mean, this is almost beyond measurable. And with a shorter clamp here, we have an error that's on the level of our calibration spec. We don't calibrate to salinity, of course, but a rough estimate of the accuracy for our salinity measurements are 0.003. Okay, and so a 75 millimeter clamp will still barely keep you within your calibration spec. And there are times when even larger errors are not necessarily important. So we have, if you know Rocky Geyer, he works in estuaries, and of course the conductivity change in an estuary is tremendous in some of them. And so Rocky, for example, mounts our instruments on a solid mast, and the cell is quite close to an even larger, chunk of metal, and it's, what he's concerned with mostly is just changes in salinity, and so those are the types of things we're actually going to measure still quite accurately, even with near field disturbance. So whether or not this actually matters depends a lot on your science. Okay. Right. Moving on, let's get a little bit into the accuracy, resolution, and stability of these types of conductivity cells. And if you just look at the basics from our specifications, we calibrate to within 0.003 millisiemens per centimeter, which as I guess I mentioned on the last slide is something like 0.003 in salinity, depending on the temperature and so forth. But that's valid over a range of 0, basically 0 to 85. So that covers most natural waters. The instrument's precise to about 0.001, and we state that the stability of the measure of conductivity is good to 0.01 millisiemens per centimeter per year. So that's a couple of times the calibration accuracy in 1 year. In fact, that's a rather conservative estimate. So I wanted to point out a case where we were able to resolve some very fine structure in natural waters to highlight the sort of resolution we can achieve with our instruments. And so a couple of years ago, I guess it was about 3 years ago now, I had a chance I should have mentioned this before. I'm actually based in Vancouver, down here in BC, And I had a chance to accompany Rich Pavlovich, who's here at UBC, on a trip to Powell Lake, BC. So Powell Lake is this kind of strangely shaped lake on the coast of BC, a couple, 100 kilometers north, or a few hundred kilometers northwest of Vancouver, on the Sunshine Coast. Powell Lake used to be a fjord 10,000 years ago, before the land rebounded. Question about the time response. Conductivity is a very, very fast time response as a sort of an electrically based measurement. It's faster than typical thermistors, so it's it's tens to 100 milliseconds or so, probably. Usually we're more concerned with the time response of the thermistor. Does that answer your question, Felipe? So moving back here, so this is a very interesting lake, because it has basically a lens of fresh water on the top, and it's geothermally heated from below. And because it was a fjord 10,000 years ago, the bottom of it's filled with seawater that's been removed, which has been out of contact with the actual ocean at large for 10,000 years, which means there's some very interesting biogeochemistry happening at the bottom of the lake. If you send a bottle to the bottom of this lake and bring it up to the surface, it fizzes methane gas, it bubbles methane gas out of it, because of the biogeochemistry and the fact that the depths of this lake have been isolated from the atmosphere for 10,000 years. But actually, because it's geothermally heated and salty at the bottom, it sets up the diffusive instability, and that results in some very interesting thermohaline structure. So what we did is we simply, here's a large instrument package containing a Siebert 25 and many other instruments here. And with $50,000 of instruments, we used hose clamps and tape, like good field oceanographers, to attach an RBR CTD at the end here. But here was the result. So near the base of this lake, we have these diffusive steps, okay? The lake's about 330 meters deep. And on the left panel, I have a profile from 325 to 335, anyways, 10 meters of the water column, of conductivity and temperature, okay? And I've plotted the RBR and the Siebert here, blue and red. But what I want to point out is that what we're able to resolve is very fine structure, as well as the Siebert 25, for example, in this particular case, right? So the red curve is the RBR data, and the blue curve is the Siebert data. Now I've done some post-processing here. The RBR was sampling at 12 hertz, so our noise floor is a little higher. But I just sample quickly, as fast as possible, and I do some averaging to bring down the noise. And so what we can see is we have these small layers a meter thick that are uniform in temperature and salinity. Right here I'm showing conductivity as the measured value. They're separated by these little 10 centimeter thick interfaces. We resolve those. We get the same value for that gradient. And these layers are different in temperature by millidegrees, and in salinity just a few parts per 0.002, as small as 0.002 in salinity, and we resolve these measurements. And I find this particularly interesting because we have a conductivity cell that has kind of a radius of influence of 10 or 15 centimeters, but we're still resolving those measurements. And I think the reason that we do that is because the bulk of the measurement from our instrument, from the conductivity cell, comes from within the conductivity cell itself, in the hole through the cell. So even though, again, there's this sort of finite 15 centimeter radius of influence around the cell, 80% or thereabouts of the signal comes from within the conductivity cell itself, which is only a few centimeters long. And so that's why I believe we resolve these real fine steps. Okay. So that's just an illustration of the sort of resolution we can get from the instrument. Long-term sensor stability is one other thing that we can address. We can look at this in two different ways. We have, of course, we have calibration lab data here, where customers return instruments and we're able to measure the error sort of year after year for different instruments, and then just compute roughly the change between calibration intervals. And we get the following histogram. So there's something like, I don't know, 100 instruments or so in this histogram. And then what we've estimated is a drift rate, so the difference in calibration errors between service intervals. And the average of this is quite close to zero, but so that's this value. So many instruments have very, very small drift, but there's a spread in that number, of course. So if you want to use a standard deviation, sort of 0.004. But what we can do from this is 0.003 is our accuracy. So if you look at how many instruments drift outside of our accuracy in a year, only 70% stay within calibration accuracy in a year. 30% drift faster. And recall what we actually put on our spec sheet is 0.01 millisiemens per centimeter per year. So there's one way to look at it. I'm going to move ahead just so we can finish and take time for some questions. We also have been involved in the Argo program, and we're putting RBR CTDs on numerous Argo floats. And so this is a rather complex analysis of the performance of one particular float that was deployed by China Argo a little more than a year ago now, January 2018. And so we have a manuscript we're writing that highlights the performance, in particular the long-term stability of the CTD measurements from the RBR CTD on an Argo float. And the results have been very encouraging so far. So one thing you might worry about in Argo, is if the CTD is in the water for years at a time, is it not susceptible to biofouling? And in this case, the answer we arrive is no. I mean, the RSL is susceptible to biofouling, but when you park as an Argo float does, it parks at 1,000 decibars, and it spends very little time near the surface where you would actually accumulate biofilms. And so in the case of Argo, where we park very deeply, 1,000 meters, we don't have any measurable biofouling at all. And so, this is a salinity anomaly plot showing the measurement versus different Argo reference database. And this slide was to show that although there appears to be a deviation from which you might say is fouling, it turns out that other floats in the region actually measured the same thing. So in fact, you have to be careful in interpreting these plots, because you'd think, although this might indicate a problem with the cell fouling and so forth, turns out other floats in the area are doing the same thing, which just means there's oceanographic variability in this region that's not captured by the reference databases. Yeah, and so actually that's it. That's the last slide for me. So that's right up till 9:30. I think it's probably time to take questions. I know that there have been many questions in the chat window, and Greg, it looks like Greg has addressed some of them.
Hello?
Yes.
What about the accuracy of the salinity? In your paper, you write about this, the accuracy of the salinity when you combine the temperature and conductivity accuracy.
Yeah, that's right. Yeah, of course. So salinity, of course, is a derived measurement, but roughly speaking, if temperature is calibrated to 0.002 degrees, and conductivity is calibrated to 0.003 or less, and so, I mean, roughly speaking, you get about 0.003 accuracy in salinity. It depends a little bit on the water temperature in that particular case, but so for the 15-degree water, at 35 parts per thousand salinity, you would expect an error of about 0.003. Does that answer your question, though?
Yeah, so it's okay.
Yep.
That's why I have interest to know how you calculate this accuracy. But I will read you an email later. Okay.
Okay. Yeah. Of course. Yep. Be happy to answer.
Yeah, I had a question on the proximity effect. So you guys sort of saw when you were within 10 centimeters of the air-sea interface, you were getting your conductivity measurements were sort of bad. The group I work with, we do a lot under ice. So would we expect something similar within that 10 to 15 centimeter range of the ice ocean interface? Our conductivity measurements might start to go bad.
Yeah, I suspect. I mean, ice. Yeah, how conductive is ice? I mean, I guess it's mostly fresh water, right? So, but I don't know if I'm not sure the physics of the conductivity of ice.
Yeah.
But yeah, I mean, as a rule of thumb, any object, yeah, I mean, anything within 15 centimeters will disturb the measurement. And so I would say you're going to be relatively safe. That's a tricky one too, because then you might have a little bit of melting in a little freshwater lens too. But anyways, yeah. I don't have an easy answer for that one right offhand.
Yeah, it would depend on the physical environment, whether the ocean was relatively warm or pretty cold near the freezing point. Yeah, I don't know. That'd be an interesting calibration experiment, wouldn't it?
Mm-hmm, sure. Mm-hmm.
All right, thank you.
Mm-hmm.
Yes, so I was just wondering, so about calibrations, if I were to order, say, some floats like the ones on the picture here, which have an antenna close to the sensor, will it normally come calibrated to take that into account, or is that up to the float manufacturer, or how would it normally be supplied?
Yeah, so I'm gonna we would actually calibrate the CTD on the float head.
Mark, would you like me to handle that?
Yeah, you know more about this, the calibration procedure, Greg. So Greg will take care of this one.
Let me just see if I can flip to. Can you stop sharing your screen there, Mark?
Yep. There you go.
And maybe this works. Can people see me? Somebody see me? Mark, can you see me?
Yes, I saw you. Yep.
Okay, perfect. So the way this works for an Argo float is that we generally either make or receive from the float manufacturer the head itself, and we install the CTD sensors on the outside, hang the electronics on the inside, and then add to the sensor head all of the normal components that are installed in use. So for instance, an Iridium or Argos antenna, an optode mast, as Mark was referring to earlier. And we calibrate with those in situ. And then we remove the antenna, which we keep here, and we simply ship back to the float manufacturer the head with the CTD. And when they add the antenna themselves, assuming that the antenna goes back into the same place that their example antenna went into, it comes out fine. We recently did some work with a French manufacturer of floats, shall we say, and they wanted us to evaluate the difference between having an optode mast in place and not in place. And that optode mast is about the diameter of a pen, and it was about 10 centimeters away from the cell. And that usually would cause us concern. However, because it's quite thin in size, we actually could not detect the presence of the optode mast with or without in conductivity or salinity. And so that meant that the float manufacturer can keep the heads in stock and decide to add the optode at the time of shipping without having to recalibrate. Does that answer your question?
Yes, thank you very much.
Let me answer a couple of other questions that were asked. Some of them were asked privately. There was some interest in the thermistor housings. This is our standard thermistor housing. This part at the bottom we call the boss, and this goes into the instrument. And then the thermistor itself is inserted through the hole in the bottom, and the thermistor goes up to the top. And that particular thermistor, I think, Ben, you were asking about the size of it. You can see it on the camera, and I'm holding it here. And so this thermistor inserts inside. Sorry about my background effects, which are probably causing confusion. By contrast to our standard thermistor, this is our fast thermistor. Our fast thermistor is much more like a hypodermic syringe. And I'm going to show you, although you're going to have to take it as read, the thermistors that go inside that hole. And so inside this gel pack, there are 10 thermistors. And you might just be able to see one there. Looks like a little worm just below my index finger. So both the thermistor and the thermistor housing change depending on whether we're doing long-term or moored measurements, as we do. So we use the standard thermistor, which is titanium and is effectively non-corrosion proof. We use that for the Argo program and any moored deployments, where they're only profiling at about 10 centimeters per second. But if you want to profile at something more like a rosette at 1 meter per second, then we use the fast thermistor, which gives a much faster time constant, about 70 milliseconds. But it is made of stainless steel. And most of you will know stainless steel is not recommended for long-term immersion. You tend to get crevice corrosion and other problems. The slides, yes, thanks for your question, Pete. The slides, we will make these available afterwards to people who are interested. And the whole thing will be up on, we'll put the presentation up as well on probably on YouTube, I think Eric was planning. Pat, thanks for your question. There was, the question was, what does the L3 mean in RBR L3 loggers? And this actually is what we more generally term generation 3. So broadly speaking, there have been 3 generations of instruments made by RBR. L2 loggers were the standard instruments, and we had LL2, which was large logger 2, and SL2, which was small logger. Now we're into the 3rd generation, and so that's where the 3 moniker comes from. You'll see it on the branding of the instruments. It looks like the cube, it's superscript 3. But you'll also see it, for instance, in the part numbers that the instruments come with. And the main differentiators of the generation 3 are that the instruments have USB-C connectors throughout. So it makes it very convenient using the bidirectional USB connector that's available everywhere, and then any AA battery. So that means you can power them off, of course, the lithium thionyl chlorides for the longest deployments, lithium ion, the so-called Energizer Ultimate batteries, which are available in supermarkets. They're not quite as long-lasting, but they're better than alkalines, which themselves are better than nickel metal hydride, which is the lowest capacity, but of course nickel metal hydride, or NiMH, has the advantage of being able to be recharged. And so if you're doing deployments every day, then NiMH means you can prevent a lot of batteries from ending up in landfill. If you're doing a long-term deployment, then of course you want to go through the expense and hassle of getting lithium thionyl chloride batteries, because they will give you 2 or 3 times the length of deployment that you would otherwise. Mark, are you still looking at some of these questions?
Yeah, I am. Yeah, I had a question from Eric. Eric, nice to see you, Eric. It's been a while since we've seen each other. But you asked if there's any pressure effects on the conductivity cell, and there is. And so we take this into account during the calibration. Yep. a question from Sorav. If I remember correctly, there was a mooring deployed at Powell Lake. Have you compared the temporal variability of the CTD with the standard CTD? There indeed was a mooring in Powell Lake. I have not done any work beyond what I showed you, but there was a master's thesis written using the data from that mooring, so I can point to that. Okay.
I could add to Bastian's question about legatos. He was interested in the proximity effect on the RBR legato, which is our CTD for use in gliders. And I have one of those here in front of me. Not probably appearing very well because of the silly background thing, which will turn off. Let's see if I can do that quickly. There we go. There you go. There's a legato with pressure sensor at the front, temperature, and the inline conductivity cell. When we do the correction factors for those, we actually started doing them with Kongsberg. And so the correction factor we very creatively called the K factor. And so legatos are characterized for the individual form factors of the gliders that they go into. Those can be switched as well. So there are some glider companies that mount them both in the bow and the stern of the vehicle. And depending on whether there are gross physical changes, then just a change of K factor takes that correction out. And as I was pointing out in my question earlier, that is largely, it is full stop additive in salinity and multiplicative in conductivity.
I had a question here on the maximum recommended duration that an RBR or CTD can be deployed in shallow water, on a shallow water mooring. My reaction is that my answer is that it depends entirely on the amount of growth in the area and what sort of critters can grow or attach to the cell. Yeah, it's a very difficult one to answer.
We do not recommend RBR for use on long-term deployments in highly fouled environments. We think that there are, we would rather recommend, and in fact, one of our mantras is that your success in deployment is our overriding goal. And we don't think that you're going to be successful doing a long-term, well-lit, warm water deployment in biologically active waters because the fouling will be too great. And so at the moment, we would recommend that you look elsewhere.
There are some environments like a very highly turbid estuary where there's a huge signal in salinity and therefore conductivity and maybe not a lot of growth because of the turbidity. Some people use them successfully there. But yeah, like Greg said, in a well-lit area, I wouldn't recommend it.
Before Ben's question disappears off the top, what about the same legato on an identical but different glider? So this K factor that we talked about, this is a characterization for the glider type, not the glider serial number. So this is actually completely shared over the geometry. So if you've put the RBR legato on a sea glider, you can mount it on any sea glider you like without any further changes. You need to just make sure the K factor for the sea glider is in there. Justin Lawrence, transferable offsets.
There was one question we should that we should answer regarding the proximity effect and mooring cages, protective cages. I'm going back. Do you have any data on the error from metal such as cages? Since metal causes higher bias, I just wanted to get an idea of how much higher the error is. Oh boy, because all cages are different and how close they are in their construction to the cell.
But in general, most people are building cages that have kind of a 10 centimeter radius around the, people don't generally make cages that are much smaller than that because they tend to get not be very effective as cages for protection. We would have to get back to you with some numbers from our calibration lab because we calibrate in cages for people all the time, and we could give you some idea as to what the offset is that we see there. We'll take one more question. Nikolai, adding to the glider questions, how do you switch the K factor on the glider? if you are talking to, so all of our instruments, every single one of our instruments can be spoken to with one user interface, which is called Ruskin. You can download Ruskin from our website under abr-global.com/products/software. Ruskin runs on a Mac or a PC. There's also a version that runs on iPhone and Android that you can get from the respective app stores, which communicates over Wi-Fi. But the entire suite of instruments that can be handled by Ruskin allows you to talk to them using a GUI, using point and click kind of mouse setup. However, under the hood, every instrument is exposing a terminal interface effectively. Whether it's USB and we expose it as a virtual COM port, or whether you might choose to connect to an instrument as you do on a glider with RS-232 or a logic level UART connection. The interface is identical. So Ruskin has the ability to change the K factor on glider CTDs in a drag and drop kind of drop down menu. But if you don't wish to use that, or you wish to do it from within the glider or some other terminal program, you can do that. And there's a command line interface for that. Hopefully that answers your question, Nikolai. Post calibration from Ben. Yes, absolutely. You can post calibrate anything you like. So all of our instruments, if you store the data in raw mode, what you're storing in what we call the desktop format is really a raw reading out of the electronics. We often refer to it as the voltage ratio internally. And the calibration coefficients are stored in the instrument, so they can be downloaded at the time of downloading the data. However, you're not obliged to use those calibration coefficients to correct or to change the raw data to engineering units. You can use any others. So if you wish to calibrate afterwards and then change the calibration coefficients and reapply them to the data set, you can do that. Yes, exactly. And that would happen if something happens in the field that you didn't expect. Mike Morley.
Yeah.
So piggyback sensors, in fact, it depends on where you place the sensor, Mike. So if the sensor is placed, let me find a conductivity cell. Here's a conductivity cell. If I place the optode right next to it, then yes, absolutely, you will see a difference that will be measurable. If it is, our rule of thumb, of course, is 15 centimeters, but let's say if you place it approximately 15 centimeters apart, you won't see anything. If you happen to place it lower, for instance, usually the instrument body, the instrument housing is below the CT cell, then we don't see it at all. The same occurs on a glider, that the induced electric current that's in the water circulates around horizontally and vertically over this cell. It doesn't circulate below. So it doesn't really matter what you have in the wet bay underneath this instrument. You could have battery packs, all those kinds of things, and it makes no difference at all. It's really things that are only, they must be in the water and they must be in the kind of area of field concentration to be detected. Electric currents from Ben. No, the only electric currents that we are sensitive to with the conductivity sensor are those that we make ourselves. So if you had, for instance, a ground leak from, let's say you were mounting next to an oil well or something that happened to have a ground leak from an AC source at 60 hertz or 50 hertz, you won't see any difference at all to our conductivity reading. There is, however, one sensor that is susceptible to stray electric currents, and that's pH. We typically use a pH electrode, and a pH electrode is an extraordinarily sensitive detector of ground leaks. So if you ever have ground fault on your observatory, deploying an electrode-based pH sensor is the way to find them, because you can find them about a mile away, it seems.
the signal, so if you have two RBR conductivity cells near to each other, like Greg mentioned, they do interfere. And you do, in that case, you get, what you'll see in conductivity is a very high frequency oscillation of a very kind of regular period. So it's easy to see in your data whether or not you put the two sensors too close, two RBR conductivity sensors too close to each other.
So we're at the 50-minute point. I think we're going to wrap up there. Thank you, everybody, for turning up. 100 of you, if the numbers were correct, and appreciate that. We will try and run a second session for anybody who didn't make it today. So if you shared your invite to other people, then we'll be coordinating a second session or a second showing of Mark's talk at some point in the near future. And we will be doing this regularly, once a week, for the next several weeks as we're all in the same situation together. Thank you, everybody, for your time, and we'll see you next time.
Bye.
Bye-bye.
Bye, thank you.
Bye, Jose.
Bye, bye, Canada.
Bye, Eric.
Thank you, Mark.
Bye-bye.
Bye, Pavel.
Bye, Mark.
Thank you, Mark. Bye.
Bye-bye. You're welcome.
Bye, Viaya. Bye, Alessandro. Bye, Long Ziwang. Goodbye, Anna. Goodbye, Sujit. Goodbye, Ali. Goodbye, Max. Goodbye,
Sorry.
Kristen.
One more quick question I've just remembered.
Of course.
To the Alzheimer Sea Explorer guys this morning, and we're hoping to pick up 4 or 5 RBR legatos. Do you know what your lead times are at the moment?
Into France.
Yes, France, and then moving on to Sweden.
So the Sweden part, of course, isn't that problematic, but getting things in and out of France right now is trickier. So usually our lead times are between 4 and 6 weeks. Of course, at the moment, anything could change because if we get somebody within the factory who's infected, we'll need to shut down half of our shifts. We're running split shifts at the moment to reduce the chance of that causing complete stoppage. So it would be difficult to give you an accurate number. You want how many units? 4 or 5?
I think the Alzheimer guys have already ordered 4, and we might be adding a 5th one on imminently.
Okay, so if it's just adding 1, then I don't imagine it's, depending on where the Alzheimer work order is at, if it's relatively early days, then adding an additional unit shouldn't make any change to the lead time. But if we're already in, for instance, the 3rd or the 4th week since the order came in, then it will be a new build, and we'd have to check into the production load at the moment.
Cool.
If you write to info@rbr-global.com, they'll be able to give you accurate lead times for the current state.
Well, I'll let the Alzheimer guys pick that up.
Okay, great. Thanks
Cool.
for your
Thank you very much, guys. It's great.
Okay.
You've got 18 more goodbyes to do, Greg.
Oh, I've said goodbye to some of these folks already. They're just not listening to me.
I'm saving the questions from the chat to review afterwards in the odd case that we might have missed one. So I'm going to stay on until the very end.
Hey, Christian, good to have you here. Alas, Federico joining at the last moment. Phil Hosegood, good to see you. Alrighty, I'm going to stop the recording and drop out myself. Do you want to copy whatever you're going to copy? Because I think when I end the meeting, it's going to close, Kevin.
It's done. Go ahead.
Okay, off we go. we'll debrief later, I'm sure.
Okay.
Nice job, Mark.
Bye. Thanks. Bye-bye.